Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the ancient world when Earth's first forests grew taller than any building humans would ever construct. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 350 million years ago, the land breathes differently. There are no birds yet to break the silence, no mammals to rustle through undergrowth that doesn't quite exist. The air itself carries a different weight, thick with moisture that never quite condenses, never quite clears. Instead, there is only the slow creaking of wood that has never known the concept of autumn, and the gentle splash of shallow roots drinking from water that will never fully drain away. The first forests rise from Earth's swampy margins like a tentative question posed to gravity itself, a geological experiment in reaching skyward that will persist for 60 million years before the planet decides to try something else entirely. These are not the forests of familiar fairy tales or weekend hikes. No squirrels leap between branches because branches, as animals will one day understand them, barely exist yet. No songbirds announce the dawn because dawn arrives unmarked, filtering through a canopy that has never learned to change color with seasons. The trees grow as single, towering pillars, some reaching heights of 130 feet, taller than the Statue of Liberty, taller than most cathedrals humans will ever build, their crowns spreading like vast umbrellas over landscapes that stretch beyond any horizon a human eye could comprehend. Lepidodendron and sigillaria stand in endless groves, their trunks smooth and hollow, marked only by the diamond patterns of shed leaves that once wrapped them like scales, like armor that protected nothing because there was nothing yet to fear. The silence here carries a weight that no modern forest could hold. It settles into the spaces between the massive trunks like something solid, something that could almost be touched. Without the constant background symphony of insects that haven't evolved their songs yet, without the whisper of small creatures that won't exist for another 100 million years, the quiet becomes almost geological in its permanence. Only the distant splash of something large moving through shallow water breaks the stillness. Perhaps one of the early amphibians, half fish and half something else, testing the boundaries between water and what will one day be called land. Even that sound fades quickly into the humid air that hangs like a patient breath between the trees, absorbed by bark that drinks sound as readily as it drinks the endless moisture from below. The air itself tells a story that modern atmospheres have forgotten. Oxygen levels climb toward 35%, nearly twice what human lungs will one day expect, creating a world where fire burns with an intensity that would terrify any modern firefighter. Yet these forests rarely burn, protected by their own constant dampness, by the endless exhalation of moisture from millions of leaves that never learn the wisdom of dormancy. The extra oxygen feeds insects that grow to proportions that will seem impossible to future epochs. Dragonflies with wingspans approaching 3 feet patrol the humid corridors between tree trunks, their compound eyes reflecting a greenish light that filters through canopies that have never seen a winter. Scientists puzzle over how these giants managed to grow so tall on roots that penetrated only a few feet into the soft, waterlogged soil. Modern engineering would declare such proportions impossible, would demand foundations extending deep into bedrock for structures of such height. Yet here they stand, or stood for millions of years, defying every principle of structural stability that will one day govern skyscrapers and suspension bridges. The mystery lies partly in their hollow construction. These trees grow like massive reeds, their interiors empty, their walls surprisingly thin for their tremendous height. Some paleobotanists suggest the trees achieved stability through sheer density, growing so closely together that they supported each other like a vast living cathedral. Each trunk a pillar in an architectural plan drawn by evolution rather than human intention. But perhaps the greater mystery lies in their very impermanence. These are forests designed by evolution to fall, as if Earth were practicing the art of growth before learning the engineering of endurance. Most of these towering trees will topple not in storms or fires, but simply under their own ambitious weight, falling into the patient swamps that wait below like soft beds prepared for giants. The falling creates no drama, no crash of splintering wood echoing through established clearings. Instead, the giants simply lean, slowly, over decades sometimes, until they settle into the water with barely a splash, where the chemistry of preservation begins its slow, perfect work. The water that receives them carries its own peculiar properties, low in oxygen despite the oxygen-rich atmosphere above. These swamps become natural laboratories for a type of preservation that will one day power human civilization. The fallen giants settle into layers, their cellular structure slowly replaced by minerals, their wood becoming stone so gradually that the process preserves even the finest details of their original form. Somewhere beneath the surface, chemistry performs its patient alchemy, transforming sunlight stored in ancient wood into the coal that will one day heat Victorian parlors and power the first steam engines. Around the bases of the standing giants, smaller plants explore the possibilities of shade. These are Earth's first experiments with forest layers, though the understory remains sparse compared to the rich complexity that will characterize later woodlands. Seed ferns spread their delicate fronds in patterns that will disappear from the fossil record long before humans learn to read stone like history books. Small club mosses carpet the constantly moist ground, their spores drifting through air so humid it sometimes seems more liquid than gas. The entire landscape exists in a state of gentle, perpetual saturation. This is a world before seasons, before the rhythms of dormancy and renewal that will one day govern temperate forests. Growth continues year-round in the endless greenhouse climate, unmarked by the annual rings that will become nature's calendars in drier times. Time moves differently here, measured not in seasons but in the slow accumulation of organic matter, the gradual settling of one geological age into the foundations of the next. Already, though, changes stir at the margins of this waterlogged paradise. Continental drift continues its ancient dance, pushing landmasses together in the slow collision that will form Pangaea. As continents merge, climate patterns begin their own gradual shift. The endless rains that feed these swamp forests will not continue forever, though forever, in geological terms, allows for another 40 million years of patient growth, patient falling, patient preservation of what will become the fossil fuels of a much later, much drier world. The bark speaks in a language older than words, older than the concept of communication itself. Each lepidodendron trunk rises like a living tower, its surface marked by the geometric precision of diamond-shaped scars where leaves once clung before dropping into the patient waters below. These patterns repeat endlessly up the hollow columns, creating a texture that catches the filtered light and throws it back in fragments, like sunlight scattered across the surface of a very still pond. The trees wear their history on their skin, each diamond scar a moment of growth preserved in living architecture that will outlast empires that haven't been imagined yet. The trunks themselves defy every assumption about how trees should be constructed. Unlike the solid heartwood of oaks or pines that will grace future forests, these ancient giants grow hollow from the beginning, their interiors empty as cathedral spaces, their walls thin as the shell of some enormous egg. A paleobotanist examining a fossilized cross-section discovers an architecture that seems almost deliberately engineered for falling, as if evolution, in its infinite experimentation, designed these first forests to be temporary monuments, practice sketches for more permanent woodlands still millions of years in the future. Walking among them, though no creature yet walks as humans will understand walking, the hollow trunks create their own acoustic environment. Sound travels differently here, absorbed and reflected by surfaces that have never learned the density that will characterize later trees. The gentle creaking of wood under its own massive weight becomes a symphony of frequencies that no ear has yet evolved to appreciate fully. Wind, when it manages to penetrate the humid stillness, produces notes from these living flutes that range from bass tones so low they're felt rather than heard, to delicate harmonics that seem to emerge from the geometric patterns of the bark itself. The engineering of these giants puzzles modern scientists who understand the physics of tall structures. Contemporary redwoods, among Earth's tallest living things, achieve their height through centuries of careful growth, building dense, tapered trunks with extensive root systems and heartwood designed to bear enormous loads. Yet these Carboniferous towers grew to comparable heights in a fraction of the time, supported by root systems that barely scratch the surface of their waterlogged world. Some specimens reached 130 feet on roots that extended only 4 or 5 feet into the soft substrate below, creating what any modern structural engineer would recognize as a recipe for inevitable collapse. The mystery deepens when considering the rate of their growth. Without annual rings to mark the passage of seasons, without the start and stop rhythm of temperate climates, these trees grew in a constant upward push that modern plants can barely sustain for single growing seasons. Estimates suggest some of the largest specimens achieved their full height in perhaps 50 years, a pace that would exhaust most contemporary trees within decades. Yet, they sustained this growth for lifespans that may have stretched across several centuries, creating their own small climates in the spaces beneath their spreading crowns. The crowns themselves present another architectural puzzle. Unlike the branching complexity of later trees, Lepidodendron topped their single trunks with a relatively simple spray of branches, spreading like enormous feather dusters or the ribs of vast umbrellas. The branches carried narrow, grass-like leaves that seem almost delicate compared to the massive infrastructure supporting them. These leaves performed the ancient alchemy of photosynthesis under conditions that will never exist again, extracting energy from sunlight filtered through an atmosphere richer in carbon dioxide than any air humans will breathe, converting it into the carbohydrates that built these towering hollows. As the leaves aged and dropped, they left behind the diamond-shaped leaf scars that gave the bark its distinctive pattern. But the falling leaves themselves tell another story of this strange forest ecosystem. Unlike the colorful autumn displays that will characterize later deciduous forests, these leaf drops occurred continuously, year-round, in a gentle rain of green that never ceased. The fallen leaves settled into the constant moisture below, where they began their own slow journey toward preservation, adding layer upon microscopic layer to what will become some of Earth's richest coal seams. The hollow nature of the trunks created opportunities that solid trees couldn't offer. Early arthropods found shelter in the empty spaces, and fossil evidence suggests that some of these interior chambers became specialized habitats for creatures that will leave only the faintest traces in the geological record. Small amphibians may have used the hollows as refuge during the dry spells that occasionally interrupted the endless humidity. Though dry spells in this epoch meant merely days without rain rather than the months-long droughts that will characterize later climates, the very impermanence built into these structures, their hollow cores, their shallow roots, their rapid growth, suggests that evolution was experimenting with a different relationship between plants and time. These were not trees designed to outlast centuries like the bristlecone pines or coast redwoods that will eventually inherit the title of Earth's tallest living things. Instead, they were designed to grow quickly, store massive amounts of carbon in their hollow structures, and then fall gracefully into the preserving chemistry of the swamps below. Each falling giant created space for others to begin their own rapid ascent toward the humid sky, maintaining the forest canopy while continuously recycling its individual components. The sound of falling, when it came, was unlike anything a modern forest could produce. The hollow trunks, settling into soft water and softer mud, made less noise than falling solid trees would make. Instead of the sharp crack of breaking heartwood, there was only the prolonged groan of bending walls, the gentle splash of entry into water, and then a settling that might continue for months as the fallen giant slowly found its final position in the accumulating layers of organic matter. Some trees fell so slowly that smaller plants had time to adjust their growth around the descending trunks, creating fossilized scenes of forests caught in the very act of their own transformation. The diamond patterns on the bark created shadows that shifted throughout the day as the sun tracked across skies unmarked by clouds that would suggest weather patterns. Light filtered through the constant humidity created its own patterns, geometric shadows cast by geometric bark onto ground that would preserve those shadow shapes in stone for creatures hundreds of millions of years in the future to puzzle over. Wondering what kind of light could create such precise patterns in such ancient forests. The air itself breathed differently in this ancient world, carrying a richness that no modern lung has ever tasted. Oxygen levels climbed steadily toward 35% of the atmosphere, nearly double the concentration that will sustain human civilization, creating conditions that fundamentally alter the rules of life on Earth. This oxygen-drunk atmosphere supports possibilities that will seem impossible to future epochs: insects growing to the size of house cats, fires burning with intensities that would consume modern forests in hours, and respiratory systems functioning with an efficiency that borders on the miraculous. The extra oxygen changes everything about how life operates in these towering forests. Chemical reactions that struggle in the thinner atmospheres of later eras proceed with ease here, allowing metabolisms to run at rates that will become legendary in the fossil record. The massive dragonflies that patrol between the hollow trunks achieve their extraordinary size partly because their simple breathing systems, designed for much lower oxygen concentrations, suddenly find themselves operating in an atmosphere so rich it can support bodies that evolution never specifically designed for such proportions. These conditions create their own peculiar hazards. Lightning strikes in this oxygen-rich environment don't simply start fires, they detonate the very air itself in combustion events that leave behind scorch marks embedded in rocks that will puzzle geologists 300 million years later. Yet, the constant humidity of the swamp forests provides its own protection, creating a world where the fuel for such spectacular fires remains perpetually too wet to burn easily. The trees themselves exhale moisture continuously through their diamond-patterned bark, through the constant rain of falling leaves, through the very respiration of their hollow cores, breathing with the vast lungs of living wood. Scientists studying atmospheric models of this period discover that such oxygen levels require very specific conditions to maintain themselves. The burial of organic matter in the swamps removes carbon from the active atmospheric cycle, preventing the decay that would consume oxygen and return carbon dioxide to the air. It's a delicate balance. The forests create the conditions that preserve themselves, which creates the conditions that maintain the atmosphere that supports the forests. The system feeds on its own success, growing richer and more oxygen-saturated with each giant that falls into the preserving waters below. The high oxygen concentrations affect even the smallest details of forest life. Insects that will struggle to achieve flight in later, thinner atmospheres find themselves soaring effortlessly through air dense enough to support wingspans that approach the size of small aircraft. Meganeura, the giant dragonfly of this epoch, achieves wingspans of nearly 3 feet, dimensions that would be impossible in modern atmospheres where insect-breathing systems simply cannot deliver enough oxygen to support such large bodies. Here, in the oxygen-rich air between the hollow giants, these creatures patrol their aerial territories like small dragons, their compound eyes reflecting light that has traveled through an atmosphere unlike any that will exist again. The abundance of oxygen also accelerates the pace of chemical weathering, breaking down rocks and releasing minerals into the waterlogged soils at rates that will seem impossibly fast to future geologists. This enhanced weathering feeds the rapid growth of the giant trees, providing the nutrients they need to build their hollow towers in mere decades rather than the centuries required by later forest giants. The chemistry of the swamps themselves operates differently, with oxygen levels just high enough at the surface to support the complex metabolisms of the trees while remaining low enough in the deeper waters to preserve the organic matter that settles there. Fire, when it does manage to take hold despite the constant humidity, burns with an intensity that would horrify any modern firefighter. Experiments conducted by atmospheric scientists suggest that wildfires in 35% oxygen would burn so hot they could crack rocks, so fast they could outrun any creature, so completely they would leave behind landscapes scoured down to bare mineral soil. Yet evidence of such catastrophic fires remains rare in the fossil record of this epoch, suggesting that the protective humidity of the swamp forests proved remarkably effective at preventing ignition despite the explosive potential of the atmosphere itself. The trees themselves become living barometers of atmospheric chemistry. Their growth rates, preserved in the spacing of their leaf scars, reflect the availability of carbon dioxide for photosynthesis and oxygen for the complex cellular respiration that powers their rapid construction of hollow towers. Some specimens show growth spurts that coincide with brief periods of even higher oxygen concentrations, while others display the slower, steadier growth patterns of trees adapting to the gradually thickening atmosphere of their age. The oxygen-rich conditions create their own acoustic environment as well. Sound travels differently through denser air, carrying farther and with different tonal qualities than the sounds that will characterize later forests. The songs of the insects, when they finally evolve the ability to make sounds, will carry for miles through air thick enough to support frequencies that thinner atmospheres cannot sustain. The creaking of the hollow trees becomes a symphonic conversation conducted across vast distances, with trunks separated by miles, responding to each other's movements like instruments in some geological orchestra. Even the light behaves differently, scattered and filtered by air dense enough to create optical effects that will disappear when atmospheric oxygen returns to more moderate levels. Sunbeams slanting through the humid air between the giants create visible columns of illumination, thick enough to seem almost solid, bright enough to support photosynthesis even in the deep shade beneath the canopy. The filtering effect of the dense atmosphere tints everything with a slightly greenish cast, as if the entire world exists underwater, swimming in air thick enough to breathe like liquid. This atmospheric richness supports growth rates that will become impossible in later epochs: trees that achieve their full height in 50 years, insects that develop from egg to adult in weeks rather than seasons, chemical cycles that complete themselves in geological instants rather than the millions of years such processes will require when oxygen levels moderate, It's as if time itself moves faster in this oxygen-drunk world, accelerating the pace of life to rhythms that will seem frantic compared to the measured growth of future forests adapted to thinner, more challenging atmospheres. The mystery that will puzzle future atmospheric scientists lies in how such conditions came to exist at all, and why they proved so temporary. The delicate balance between organic burial, atmospheric chemistry, and forest growth that maintains these oxygen levels will prove impossible to sustain indefinitely. Already, subtle changes in continental configuration and ocean circulation patterns hint at climatic shifts that will eventually drain the swamps, expose the buried organic matter to decay, and return atmospheric oxygen to more modest concentrations that will characterize the rest of Earth's history. The swamps stretch beyond every horizon, vast wetlands that exist in a state of perpetual, patient saturation. These are not the temporary marshes that will characterize later epochs, expanding and contracting with seasonal rhythms or occasional floods. Instead, they maintain their liquid embrace year after year, decade after decade, century after century, creating conditions that will prove essential for one of the most significant geological processes in Earth's history. The water moves so slowly here that movement becomes almost theoretical, a concept rather than an observable phenomenon, flowing at rates measured in inches per year rather than the familiar rush of rivers or streams. Beneath the surface of these endless wetlands, chemistry performs its most patient work. The fallen giants that once reached toward an oxygen-rich sky now rest in water so depleted of oxygen that decay proceeds along entirely different pathways than the rapid decomposition that will characterize future forests. Without sufficient oxygen to fuel the bacteria and fungi that normally reclaim dead organic matter within years or decades, the fallen trees enter a preservation process that will require millions of years to complete, transforming slowly from wood to stone to coal, through a sequence of chemical changes so gradual they occur below the threshold of observation. The water itself carries the specific chemistry necessary for this transformation, low in dissolved oxygen but rich in the dissolved minerals leached from the surrounding landscape by atmospheric weathering. These swamp waters create an environment where organic matter accumulates faster than it decomposes. Each fallen tree, each dropped leaf, each generation of aquatic plants adds to layers that build up like pages in a book written in compressed carbon, a geological library that will one day power steam engines and heat parlors in civilizations that exist only as potential in the DNA of early amphibians. Scientists studying coal formation discover that the preservation process requires extraordinarily specific conditions. Too much oxygen, and the organic matter decays completely, returning its carbon to the atmosphere as carbon dioxide. Too little water, and the wood dries out and either burns or crumbles to dust. But here, in these carboniferous swamps, the conditions achieve a perfect balance that will prove impossible to replicate in later geological epochs. The chemistry operates like a vast, slow-motion photograph, capturing not just the form of the ancient forests, but the very cellular structure of wood that lived and breathed 350 million years ago. The accumulation happens in layers so thin that individual seasons, if seasons existed in this greenhouse world, would be represented by deposits thinner than paper. Yet, these microscopic layers, repeated across millions of years, create seams of coal dozens of feet thick, compressed libraries containing the stored sunlight of entire geological ages. The mathematics of this preservation staggers modern calculations, millions of years of forest growth compressed into layers that can be measured in meters, creating energy concentrations that will power human civilization for centuries before depleting. The swamps themselves exist in various stages of this preservation process. In some areas, Recently fallen trees still retain recognizable bark and wood structure, their hollow cores filled with water that will gradually be replaced by dissolved minerals over geological time. In deeper, older sections, the transformation has progressed through the intermediate stages: wood becoming peat, peat compressing into lignite, lignite slowly hardening into the black gold that will define the industrial age. The entire spectrum of coal formation can be observed within a single swamp system, like watching a time-lapse sequence that unfolds over millions of years. The geography of these wetlands follows patterns that will influence continental geology for hundreds of millions of years. Vast river deltas spread across low-lying coastal plains, creating networks of channels and backwaters that shift slowly as sea levels rise and fall with the rhythmic breathing of a planet still learning to regulate its climate. When sea levels rise, the swamps expand inland, drowning the bases of the giant trees and creating new areas for preservation. When levels fall, previously submerged organic matter may be exposed briefly to oxygen, halting the preservation process and creating the complex geological signatures that will help future scientists map these ancient coastlines. The chemistry of preservation operates differently in different parts of each swamp. Near the channels where water moves slightly faster, oxygen levels remain just high enough to support different types of decomposition, creating coal with different properties and mineral content. In the stagnant backwaters where water barely moves for decades at a time, preservation proceeds with almost perfect fidelity, maintaining cellular details that will astonish paleobotanists examining coal specimens under electron microscopes hundreds of millions of years later. Marine incursions add their own chemical signatures to the preservation process. When rising sea levels bring salt water into contact with the freshwater swamps, the changes in water chemistry alter the types of bacteria that can survive, changing the chemistry of decomposition and adding sulfur compounds that will give some coals their distinctive burning characteristics. These brief saltwater episodes, lasting perhaps only decades in the context of millions of years of freshwater conditions, create marker layers that will help future geologists correlate coal seams across continents. The preservation process also captures more than just trees. Insects caught in resin that hardens underwater, spores and pollen that settle into the oxygen-poor depths, even the impressions of raindrops on mud surfaces that quickly become covered by organic matter all become part of the geological record accumulating in these patient waters. Future paleontologists will find entire ecosystems preserved in the coal. Reading the history of these ancient forests like texts written in compressed carbon. The temperature of preservation matters as well. The warm climate of this epoch means that chemical reactions proceed faster than they would in cooler conditions, but the preservation chemistry still operates within narrow temperature ranges. Too warm, and even the oxygen-poor water cannot prevent decay. Too cool, and the chemical transformations that convert wood to coal proceed too slowly to keep pace with the accumulation of new organic matter. The swamps maintain temperatures that allow preservation to occur faster than decay, a delicate balance that will be lost when changing climates eventually drain these wetlands. Already, the first stages of what will become vast coal deposits begin to accumulate in the deeper parts of the swamps. Layers of compressed organic matter, still recognizably plant material, but already showing the chemical changes that lead toward coal formation, build up like slow sedimentary deposits. In some locations, these early coal precursors already measure several feet thick, representing thousands of years of patient preservation, of chemistry working so slowly that its progress can only be measured by comparing samples separated by geological ages. The irony embedded in this process will not be lost on future civilizations. The same atmospheric conditions that support the giant trees, high oxygen levels that prevent the complete decay of organic matter, create the coal deposits that will one day be burned to power machines that return that ancient carbon to the atmosphere as carbon dioxide, completing chemical cycles that span hundreds of millions of years. The forests preserve themselves through falling, creating the geological foundations for technologies that their original growth made possible. Time moves differently in a world without seasons, where growth proceeds in an endless progression unmarked by the annual rhythms that will one day govern temperate forests. The giant trees of this epoch grow without the familiar rings that will become nature's calendars, their wood forming in continuous layers that respond to changes measured not in months, but in millennia. Without the start and stop rhythm of dormancy and renewal, without the chemical signals that tell later trees when to pause their growth for winter's rest, these ancient giants push steadily skyward in a pattern of development that will seem almost alien to future botanists studying their fossilized remains. The absence of growth rings creates its own scientific mysteries. Modern dendrochronologists, accustomed to reading tree rings like historical documents that record droughts, volcanic eruptions, and climate fluctuations with annual precision, find themselves confronted by wood that offers no such temporal roadmap. The cellular structure of these carboniferous giants shows only the gradual changes that occur over geological timescales, subtle shifts in cell size and wall thickness that reflect long-term changes in atmospheric chemistry or soil conditions rather than the seasonal patterns that will characterize later forest ecosystems. Without seasonal dormancy, the trees invest their energy differently than their descendants will. Rather than storing carbohydrates in roots and trunk tissues to survive periods of cold or drought, they channel their resources into continuous upward growth, building their hollow towers with a single-minded determination that allows them to achieve remarkable heights in remarkably short periods. Some specimens may have grown several feet per year throughout their entire lifespans, a pace that would exhaust most modern trees but proves sustainable in the constant greenhouse conditions of this ancient world. The lack of seasonal rhythms affects more than just individual trees. Entire forest ecosystems operate without the synchronized timing that will coordinate later woodland communities. There are no spring migrations of insects emerging from winter dormancy, no autumn preparations for months of scarcity, no winter periods when forest metabolism slows to a barely detectable crawl. Instead, biological processes proceed at their optimal rates year-round, creating ecosystems that operate with an intensity and efficiency that will become impossible when climates develop the seasonal variations that characterize most of Earth's later history. Reproduction. In these seasonless forests follows different patterns as well. Without environmental cues that signal optimal times for producing seeds or spores, the trees release their reproductive materials continuously throughout their lifespans. This creates a constant rain of genetic material that settles into the swamp waters below, where some find suitable conditions for germination, while most becomes part of the organic matter accumulating toward coal formation. The forest floor, such as it is in these waterlogged environments, receives new seedlings year-round rather than the concentrated bursts of reproduction that will characterize seasonal ecosystems. The continuous growing season also affects the insects and other arthropods that share these forests. Without winter conditions that require hibernation or diapause, populations can expand continuously throughout the year, limited only by food availability and predation rather than seasonal bottlenecks. This may help explain the remarkable sizes achieved by some carboniferous insects. Not only do high oxygen levels support larger body sizes, but the absence of seasonal population crashes allows species to evolve along trajectories that take advantage of year-round optimal conditions. Photosynthesis itself operates differently in these seasonless forests. Modern plants time their growth to take advantage of favorable conditions and shut down during periods of cold or drought. But these ancient trees conduct photosynthesis at maximum rates continuously. The diamond-patterned bark that characterizes many species may partially reflect this difference, rather than the thick, protective bark that helps later trees survive winter conditions. These surfaces seem designed primarily for gas exchange and moisture regulation during continuous growth periods. The absence of annual rings makes it nearly impossible to determine the exact lifespans of individual trees, but indirect evidence suggests that some specimens may have lived for several centuries, remarkably long lives for organisms that grew so rapidly. Without the mechanical stress of expanding and contracting wood that comes with seasonal temperature variations, without the metabolic stress of repeatedly shutting down and restarting growth processes, these trees may have achieved longevity through the very constancy of their growing conditions. Weather patterns in this seasonless world operate on different scales than the familiar rhythms of later climates. Instead of seasonal shifts between warm and cold, wet and dry, conditions fluctuate over much longer periods, decades or centuries of slightly wetter conditions, followed by similar periods of slightly drier weather. These long-term cycles may be reflected in subtle changes in the wood structure of the trees, creating growth patterns visible only when examining specimens that live through multiple climatic cycles spanning thousands of years. The continuous nature of growth also means that forest succession operates differently than it will in seasonal environments. Without periodic disturbances like winter storms or seasonal droughts that create opportunities for new species to establish themselves, the composition of these forests may have remained remarkably stable for millions of years. The same species that first colonized the waterlogged lowlands continue to dominate them for geological ages, their success becoming self-perpetuating in the absence of seasonal pressures that might favor alternative strategies. Forest fires, rare as they are in these humid conditions, create different patterns of recovery than they will in seasonal forests. Without annual dry seasons that concentrate fire risk into predictable periods, the occasional fires that do occur come without warning and affect ecosystems that have no evolved responses to fire disturbance. Recovery must proceed entirely through immigration from undisturbed areas rather than through fire-adapted reproduction strategies, creating a patchwork of forest ages that reflects the random timing of rare fire events rather than seasonal fire cycles. The mycorrhizal relationships between tree roots and soil fungi also develop differently in these continuously warm, wet conditions. Without seasonal periods when both partners must prepare for dormancy, these symbiotic relationships can become extraordinarily intimate, with some fungi possibly living entirely within the hollow root systems of the trees, creating biological partnerships that will seem almost impossibly close to scientists studying more independent plant-fungal relationships in seasonal forests. Already, though, the climatic stability that permits this seasonless existence shows subtle signs of change. Continental drift continues its slow reshaping of global geography, gradually altering ocean circulation patterns that will eventually introduce seasonal variations to regions that have known only constant greenhouse conditions for millions of years. The trees growing now will be among the last to experience the peculiar advantages of completely seasonless growth, their wood preserving evidence of growth patterns that will never be repeated in Earth's later history. Beneath the towering hollow giants, a different world emerges in the perpetual twilight of the forest floor. Here, in the filtered green light that penetrates the constant canopy above, smaller plants explore the possibilities of life in permanent shade, creating Earth's first experiments with the layered complexity that will define forest ecosystems for hundreds of millions of years. These understory communities develop their own rhythms and relationships, adapted to light levels so low that most modern plants would struggle to survive, yet somehow managing to thrive in conditions that will never exist again in quite the same way. The canopy above filters sunlight through leaves that never change color, never fall in seasonal abundance, creating a light environment of remarkable consistency. Unlike the dramatic seasonal variations in light availability that will characterize later deciduous forests, or the steady but bright illumination beneath evergreen canopies, this understory receives a gentle, greenish luminescence that varies only with the slow passage of clouds across skies that rarely clear completely. Photosynthesis here operates at the margins of possibility, capturing the faint energy that penetrates dozens of feet of humid air and multiple layers of primitive leaves. Seed ferns spread their delicate fronds across this shadowy landscape, their lacy patterns creating a secondary canopy just a few feet above the waterlogged ground. These plants represent one of evolution's early experiments with complex leaf architecture, developing the intricate patterns that maximize surface area for light capture while minimizing the structural investment required to support such elaborate foliage. Their fronds move gently in air currents so subtle they barely qualify as breezes, creating shifting patterns of even deeper shadow that dance across the forest floor like the play of light through shallow water. The club mosses carpet the spaces between the seed ferns, forming living rugs that can extend for miles without interruption. These primitive plants, ancestors of the towering lepidodendron above but content to remain low and spreading, create their own microenvironments within the larger forest ecosystem. Their spores drift continuously through the humid air, invisible clouds of genetic material that settle into every available niche, creating a constant background of reproduction that connects distant parts of the forest through airborne genetic exchange. The forest floor itself exists as a partially submerged landscape where the distinction between land and water becomes increasingly meaningless. What might be called soil in later epochs consists here of a soft mixture of waterlogged organic matter, fine sediments, and the decomposing remains of the few plants that actually manage to complete their life cycles and die in this preserving environment. Walking here, if any creature yet possessed the anatomy for true walking, would involve splashing through shallow water punctuated by slightly more solid mounds where generations of club mosses have built up small islands of accumulated organic matter. The acoustic environment of the understory differs markedly from the echoing spaces among the hollow tree trunks above. Sound here becomes muffled, absorbed by the soft surfaces and constant moisture, creating an environment where even the smallest noises carry with unusual clarity, while larger sounds seem to disappear almost immediately. The gentle splash of something moving through the shallow water, the soft rustle of seed fern fronds brushing against each other, the barely audible pop of spores being released into the humid air. All these sounds exist in a acoustic space so quiet that silence itself becomes a presence rather than merely an absence. Light plays differently here as well, creating optical effects that will disappear when forest understories develop the complex architecture of later epochs. Beams of sunlight, when they manage to penetrate the multiple layers above, become visible as distinct columns in the humid air, thick enough to seem almost solid, bright enough to support brief moments of more intense photosynthesis for any plant fortunate enough to intercept them. These light shafts move slowly across the understory as the sun tracks overhead, creating a subtle rhythm of illumination that represents the closest thing to temporal variation in this seasonless world. The relationships between understory plants operate according to principles that will seem familiar to students of later forest ecology, yet with important differences imposed by the unique conditions of this epoch. Competition for light occurs, but proceeds much more slowly than in the dynamic understories of seasonal forests. Plants that gain access to slightly better illumination maintain their advantage for decades or centuries, gradually expanding their territory through growth patterns so slow they're barely detectable within individual lifespans. Water availability. The factor that limits plant growth in most later ecosystems presents no constraints here. Instead, understory plants must cope with too much water, developing strategies for surviving in conditions where their roots exist in permanent saturation. Some species develop hollow root systems that echo the architecture of the giant trees above, allowing air circulation through their underground structures. Others develop symbiotic relationships with bacteria that can fix nitrogen even in waterlogged soils, creating partnerships that will become essential when later ecosystems face the combined challenges of seasonal drought and nitrogen limitation. The nutrient cycles of the understory operate with unusual efficiency in these constantly wet conditions. Decomposition proceeds slowly in the oxygen-poor environment, but the constant moisture allows dissolved nutrients to move freely between plants and soil, creating a system where chemical resources circulate rapidly through the living components of the ecosystem while being preserved in the non-living organic matter that accumulates toward coal formation. This creates forests that are simultaneously highly productive and highly conservative, growing rapidly while preserving most of their organic matter for geological timescales. Insects and other arthropods find in the understory a three-dimensional habitat of extraordinary complexity. The layered architecture of seed ferns creates countless niches for small creatures, while the club moss carpets provide hiding places and hunting grounds for predators and prey. Some insects specialize in particular layers of the understory, spending their entire life cycles within vertical zones only a few feet thick, developing relationships with specific plants that will persist for millions of years of coevolution. The reproductive strategies of understory plants reflect the unique challenges of their environment. Spores and seeds must germinate successfully in near darkness and permanent saturation, conditions that will prove impossible for most later plant species. This selects for reproductive strategies based on producing enormous numbers of spores or seeds, flooding the environment with genetic material in the hope that some will find the rare microsites where establishment proves possible. Already, the understory plants begin to exhibit the first signs of the complex vertical stratification that will characterize later forest ecosystems. Some species specialize in the deepest shade, developing leaf chemistry that can extract energy from light so dim it barely registers on instruments designed to measure illumination. Others concentrate near the margins where tree falls occasionally create brief gaps in the canopy, developing rapid growth strategies that can take advantage of temporary increases in light availability. The future of these understory communities remains tied to the fate of the giant trees above. As long as the hollow towers continue to provide stable canopy conditions, these shade-adapted plants can continue their slow exploration of life in permanent twilight. But changes in climate that affect the giants will inevitably transform the light environment below, setting the stage for the evolution of entirely new understory strategies adapted to more variable conditions. The engineering principles that govern these ancient forests would confound any modern structural engineer. Trees reaching heights of 130 feet stand on root systems that penetrate barely 4 or 5 feet into the soft, waterlogged substrate beneath them, creating proportions that violate every rule of structural stability that will govern skyscrapers and suspension bridges in distant civilizations. Yet, these impossible giants persist for millions of years, their shallow foundations somehow adequate to anchor hollow towers that sway gently in breezes that would topple any building designed with similar proportions. The root systems themselves represent a compromise between the need for anchorage and the realities of permanently saturated soils. Unlike the deep taproots that will characterize trees adapted to seasonal droughts, or the wide-spreading surface roots that will support later forest giants, these carboniferous roots grow in horizontal mats that extend laterally for considerable distances while barely penetrating the waterlogged sediments below. The roots must extract oxygen from soils where oxygen exists only in the thinnest surface layers, developing specialized tissues that transport air from above-ground portions of the tree down to the submerged root tips. Scientists studying the mechanics of these root systems discover adaptations that seem almost designed for instability. The roots develop little of the woody strength that will characterize later tree support systems, remaining relatively soft and flexible throughout their growth. This flexibility may actually contribute to the tree's stability, allowing the entire root system to move as a unit when wind forces act on the massive canopies above, distributing stress across wide areas rather than concentrating it at particular attachment points where rigid roots might snap under pressure. The waterlogged environment creates its own form of support for the shallow root systems. The saturated soil surrounding the roots provides lateral resistance to movement, acting like a liquid foundation that flows around and supports the root structures. When trees do fall, examination of their root systems reveals that failure typically occurs not through the breaking of individual roots, but through the gradual tilting of entire root masses as the soft substrate slowly gives way under the enormous loads imposed by the hollow towers above. The mathematics of this instability creates its own peculiar stability. Trees growing in dense stands support each other through their interlocking canopies, creating structural networks where individual giants lean against their neighbors, distributing the loads imposed by wind and their own weight across multiple trunks. When one tree begins to lean, its neighbors adjust their own growth patterns to provide counter-support, creating forests that function as single, vast structural systems rather than collections of independent trees. Root competition in these shallow systems operates according to principles that will seem alien to students of later forest ecology. With all trees drawing resources from the same thin surface layer of soil, root systems interweave so thoroughly that individual trees become difficult to distinguish below ground. Some paleobotanists suggest that the largest forest stands may have functioned almost like single organisms, sharing resources through their interconnected root networks and responding to environmental stresses as unified systems rather than competing individuals. The chemical environment of the root zone presents its own challenges and opportunities. With oxygen levels near zero, just inches below the surface, roots must rely on specialized bacterial partnerships to obtain nitrogen and other essential nutrients. These bacterial relationships operate more intimately than the mycorrhizal partnerships that will characterize later forests, with some bacteria living entirely within root tissues and sharing metabolic processes with their plant hosts. The chemistry of these partnerships creates soil conditions that further encourage the preservation of organic matter, contributing to the coal-forming processes occurring throughout these ancient wetlands. Water uptake in permanently saturated soils requires different strategies than the water mining that will characterize trees adapted to seasonal droughts. Rather than developing extensive root systems designed to capture rare rainfall or groundwater, these trees must regulate water intake to prevent drowning, developing root barriers and transport systems that can exclude excess water while still obtaining dissolved nutrients. The constant availability of water allows rapid growth, but also creates the need for sophisticated internal drainage systems that prevent waterlogging of the tree's own tissues. The seasonal flooding that periodically raises water levels even higher than their normal saturation points forces additional adaptations. When floodwaters rise high enough to submerge the lower portions of tree trunks, the trees must rely entirely on their hollow interior spaces for air transport to their roots. Some species develop specialized breathing roots that grow upward from the main root system, creating snorkel-like structures that can maintain air circulation even when normal soil surfaces disappear under seasonal high water. The geometry of root spread influences forest spacing in ways that create surprisingly regular patterns across vast landscapes. Trees must space themselves far enough apart to avoid complete overlap of their shallow root systems, yet close enough together to provide mutual support through canopy contact. This creates forests with almost mathematical regularity in tree spacing, visible in fossil evidence as patterns of preserved root systems that maintained consistent distances across areas measured in square miles. Nutrient cycling through these shallow root systems operates with unusual efficiency despite the waterlogged conditions. The constant moisture allows dissolved nutrients to move freely through the soil, while the shallow root zone concentrates biological activity in a narrow band where cycling can occur rapidly. Leaves falling from the canopy above decompose slowly in the oxygen-poor conditions, but release their nutrients quickly into the shallow zone where roots can recapture them almost immediately. The instability built into these root systems may serve evolutionary purposes that won't become apparent until much later in forest evolution. Trees that fall regularly create opportunities for genetic mixing that more stable forests might not provide, while the relatively short lifespans imposed by inevitable toppling prevent any single genetic line from dominating forest stands for geological time periods. The falling trees also create the regular supply of organic matter necessary for coal formation, making the instability of individual trees essential for the long-term success of the forest ecosystem. Root fossilization in these waterlogged environments preserves details of root architecture that would be lost in better-drained soils. Future paleobotanists will find root systems preserved with cellular detail, allowing detailed study of how these trees solve the engineering challenges of growing tall on shallow foundations. The preserved root systems reveal a variety of experimental strategies, suggesting that even within single species, trees developed individual solutions to the problems of staying upright in impossible conditions. Already, some trees show evidence of developing deeper root systems, experimental adaptations that point toward the engineering solutions that will characterize later forests. These deeper roots remain rare and appear mainly in trees growing on slightly better drained sites, but they represent the beginning of evolutionary trends that will eventually produce the deeply anchored trees capable of surviving in seasonal climates where surface soils dry out regularly. In the oxygen-poor depths beneath the forest floor, a revolution in decomposition unfolds so slowly that its implications will not become apparent for millions of years. The white rot fungi that will one day efficiently dismantle lignin, the complex polymer that gives wood its strength and durability, have not yet evolved the enzymatic machinery necessary to break down this fundamental component of tree architecture. Without these microscopic decomposers, the fallen giants of the Carboniferous forests accumulate in ways that will seem impossible to future ecologists accustomed to forests where dead wood disappears within decades of falling. Linen itself represents one of evolution's most successful structural innovations, a three-dimensional polymer that provides the mechanical strength necessary for trees to grow to extraordinary heights while remaining relatively lightweight. Yet this same chemical innovation creates an unexpected consequence in an epoch where the biological machinery for lignin decomposition simply doesn't exist yet. The hollow trunks that crash into the patient swamps below bring with them cellular walls reinforced with lignin polymers that resist every form of decay available in this ancient world, creating the raw material for coal formation on a scale that will never be repeated. The few fungi that do exist in these waterlogged environments possess only the most primitive decomposition capabilities, able to break down simple carbohydrates and proteins, but completely unable to access the energy stored in lignin molecules. This creates a peculiar form of partial decomposition where the soft tissues of fallen trees disappear relatively quickly, leaving behind the lignin-rich structural components that will form the backbone of future coal seams. The selectivity of this incomplete decay process concentrates lignin in the accumulating organic matter, creating deposits with energy densities that will seem almost impossibly high to future civilizations. Scientists studying the evolution of lignin decomposition discover that white rot fungi require highly specialized enzymes that won't appear for another 60 million years. These enzymes must operate in the presence of oxygen to function properly. Yet the swamp environments where most decomposition occurs maintain oxygen levels too low to support such biochemistry, even if the enzymes existed. This creates a perfect storm of chemical conditions where lignin accumulates not because of any single factor, but because of the intersection of atmospheric chemistry, fungal evolution, and environmental conditions that will prove impossible to replicate in later epochs. The absence of efficient lignin decomposition affects more than just the rate of coal formation. It fundamentally alters the nutrient cycles of these ancient forests, creating ecosystems where carbon accumulates continuously rather than being recycled rapidly through decomposer communities. Trees growing in these forests access nutrients primarily from fresh inputs, atmospheric nitrogen fixation, mineral weathering, and the slow release of nutrients from partially decomposed organic matter, rather than from the rapid recycling of recently dead material that will characterize later forest ecosystems. The chemical structure of lignin itself varies among different tree species, creating the foundation for the different types of coal that will form from different forest communities. The lignin produced by the scale trees like lepidodendron differs subtly from that created by early conifers or seed ferns, leading to coal deposits with distinctive chemical signatures that will allow future geologists to identify which types of ancient forests contributed to particular coal seams. These chemical fingerprints preserve not just the fact that forests existed, but detailed information about their species composition and growth conditions. Decomposition that does occur proceeds along entirely different pathways than the rapid recycling that will characterize later forests. Bacterial decomposition dominates in the oxygen-poor conditions, breaking down proteins and simple carbohydrates while leaving lignin structures intact. This bacterial decomposition produces methane and hydrogen sulfide as byproducts, creating chemical environments that further inhibit the evolution of more efficient decomposer organisms. The swamps become vast biochemical laboratories where organic matter experiments with preservation rather than decay. The accumulation of undecayed lignin creates physical environments unlike anything that will exist in later forest ecosystems. Fallen logs remain structurally intact for centuries, creating a three-dimensional landscape of crisscrossing trunks that provides habitat for early arthropods and creates complex flow patterns in the shallow waters. Some areas develop into vast log jams where hundreds of fallen giants create temporary dams that alter local hydrology and create new microenvironments for specialized plant communities. The energy implications of this lignin preservation stagger modern calculations. Coal deposits forming in these swamps will eventually contain energy concentrations representing millions of years of stored sunlight, compressed into geological layers that can power industrial civilizations for centuries. The absence of white rot fungi essentially removes the primary mechanism for returning this stored energy to the carbon cycle, creating what amounts to a planetary energy storage system of unprecedented scale. Some primitive fungi do attempt to decompose the lignin-rich wood, but their efforts proceed so slowly that the process takes millennia rather than the years or decades required by later fungal communities. These early attempts at lignin decomposition leave characteristic patterns in the wood that will be preserved in coal formations, creating microscopic evidence of the evolutionary struggle between chemical innovation and biological adaptation that characterize this epoch. The chemical environment created by accumulating lignin also affects the preservation of other organic materials. Proteins and other molecules that would normally decompose rapidly find themselves protected by the lignin matrix, leading to exceptional preservation of cellular details that will provide future paleobiologists with unprecedented insights into the biochemistry of these ancient forests. Some coal deposits will preserve molecular fossils that retain identifiable fragments of original proteins and other biomolecules. The absence of efficient decomposition creates feedback loops that accelerate the preservation process. As lignin-rich organic matter accumulates, it creates increasingly anaerobic conditions that further inhibit decomposition while promoting the chemical transformations that lead toward coal formation. The forests essentially create the conditions that ensure their own preservation, building geological monuments to their own existence through the simple absence of the biological machinery necessary for complete decay. Already, early experiments in lignin decomposition begin to appear in some fungal lineages. Evolutionary innovations that point toward the biochemical revolutions that will eventually drain these swamps by making efficient wood decomposition possible. But these experimental decomposers remain rare and inefficient, unable to keep pace with the massive inputs of lignin-rich wood produced by the giant trees above. Their future success will fundamentally alter the global carbon cycle, but for now, they represent only the faintest hint of ecological changes still millions of years in the future. The lignin accumulating in these swamps represents more than just stored energy. It preserves a record of atmospheric carbon dioxide concentrations, climate conditions, and even the cellular biology of trees that will be extinct for hundreds of millions of years by the time humans develop the technology to read these chemical libraries embedded in stone. Above the patient swamps, in the humid corridors between the hollow giants, arthropods achieve proportions that will seem impossible to every future epoch. Dragonflies with wingspans approaching 3 feet patrol territories measured in square miles, their compound eyes reflecting light filtered through canopies that have never known winter. These aerial giants navigate through air thick enough to support flight strategies that will become unthinkable when atmospheric oxygen returns to more modest concentrations, creating an age of insects that dwarfs anything that will follow in the fossil record. Meganeura, the giant dragonfly of this epoch, represents the extreme end of what insect respiratory systems can achieve when atmospheric oxygen reaches 35% of the total atmosphere. Modern dragonflies, magnificent as they are, struggle to achieve wingspans much beyond 6 inches because their primitive breathing systems, networks of tubes that deliver oxygen directly to tissues without the benefit of lungs or circulatory systems, simply cannot transport enough oxygen to support larger bodies in modern 21% oxygen atmospheres. But here, in the oxygen-drunk air of the Carboniferous forests, these same respiratory systems find themselves operating in an atmospheric environment so rich they can support bodies that approach the size of small birds. The physics of flight operates differently in these dense atmospheric conditions. Wings designed for much thinner air suddenly find themselves with extraordinary lifting power, allowing insects to achieve flight patterns that seem almost effortless compared to the energetic demands of flight in later atmospheres. Some of the giant dragonflies appear to soar for hours without visible wing beats, riding air currents dense enough to provide lift with minimal energy expenditure. The acoustic environment of their flight creates sounds unlike anything later insects will produce. The deep humming of wings large enough to move substantial volumes of thick air, creating frequencies that carry for miles through the humid spaces between trees. Millipedes in these forests achieve lengths that rival small snakes, their segmented bodies growing to 6 feet or more as they browse through the endless supply of partially decayed organic matter accumulating on the forest floor. Arthropleura, the giant millipede of this epoch, develops exoskeletons that provide structural support for bodies that would collapse under their own weight in the thinner atmospheres of later epochs. These creatures create their own pathways through the waterlogged forests, leaving trackways that will be preserved in the soft sediments and discovered by paleontologists hundreds of millions of years later. The giant insects create their own ecological relationships that will disappear when oxygen levels moderate. Predator-prey dynamics operate on scales that dwarf the interactions between later insect communities. Giant dragonflies hunt prey that includes early amphibians, while massive ground-dwelling arthropods compete for territory with vertebrates that are themselves experimenting with life on land. The energy flows through these communities involve biomass transfers that will seem enormous compared to the interactions between insects and vertebrates in oxygen-limited later ecosystems. Spiders in these forests develop hunting strategies adapted to prey much larger than themselves relative to what later arachnids will encounter. Some species construct webs with silk strands strong enough to entangle insects with wingspans measured in feet rather than inches. The webs themselves become architectural marvels that span considerable distances between tree trunks, creating three-dimensional traps that take advantage of the relatively slow flight speeds possible in the dense atmosphere to capture prey that would easily break through webs designed for smaller insects. The respiratory systems that enable these giant sizes also create vulnerabilities that will prove fatal when atmospheric conditions change. Insect breathing relies on passive diffusion of oxygen through networks of increasingly narrow tubes, a system that works efficiently over short distances but becomes limiting as body size increases. In 35% oxygen atmospheres, diffusion can supply adequate oxygen to tissues several times more distant from breathing pores than will be possible in future atmospheric conditions. But the system provides no evolutionary pathway for adapting to decreasing oxygen concentrations. The giant insects also create acoustic environments that will never be replicated in later forest ecosystems. The sounds of massive wings beating through dense air, the vibrations created by 6-foot millipedes moving through leaf litter, the calls of arthropods large enough to produce sounds audible to creatures miles away, all combine to create forest soundscapes that dwarf the acoustic environments of later insect communities. Some of these sounds may have influenced the evolution of early vertebrate hearing, creating selective pressures for detecting frequencies that will disappear when the giant insects become extinct. Temperature regulation becomes a different challenge for insects operating at these larger scales. Modern insects rely primarily on behavioral strategies for temperature control, moving between sun and shade, adjusting activity levels to match ambient temperatures. But the giant arthropods of this epoch begin to approach body sizes where internal temperature regulation becomes physiologically significant. Some species may have developed primitive forms of metabolic temperature control, evolutionary experiments that point toward the more sophisticated thermoregulation that will characterize later vertebrate evolution. The feeding strategies of giant insects create impacts on forest ecosystems that approach those of large vertebrates in later epochs. Herbivorous arthropods consume vegetation at rates that significantly affect plant community composition, while predaceous species remove biomass from prey populations at scales that influence the population dynamics of early amphibians and other vertebrates. These interaction intensities will disappear when insects return to smaller sizes, leaving ecological niches that won't be filled until much larger vertebrates evolve to occupy them. Flight corridors develop between forest stands as the giant dragonflies establish territories and migration routes that span hundreds of miles. These aerial highways influence the genetic structure of insect populations across vast geographical areas, creating gene flow patterns that connect insect communities separated by distances that would completely isolate smaller insects with more limited flight capabilities. The population genetics of these giant insects operate on continental scales that will not be seen again in arthropod communities. Reproductive strategies scale up along with body sizes, with some insects producing eggs large enough to contain food reserves that support extended larval development. Giant dragonfly nymphs live underwater for years rather than months, growing through molts that each produce noticeable increases in absolute size rather than the small incremental changes characteristic of smaller insects. These extended development periods allow for complex behavioral learning that approaches what will be seen in much larger vertebrates. The evolutionary constraints that prevent insects from growing larger become apparent in the largest specimens of this epoch. Even in optimal atmospheric conditions, the insect body plan begins to approach fundamental limits imposed by the efficiency of exoskeletal support systems and the physics of gas exchange through passive diffusion. The largest insects show evidence of physiological stress that suggests they were operating near the maximum sizes possible for their basic anatomical architecture. Already, subtle changes in atmospheric oxygen concentrations begin to affect the largest insects, creating selection pressures that will eventually favor smaller body sizes. The giant forms represent an evolutionary experiment that will prove successful only under the specific atmospheric conditions of this epoch, leaving behind fossil evidence of what becomes possible when air chemistry creates opportunities that will never arise again in Earth's later history. The seas rise and fall with rhythms that dwarf any tidal cycle, breathing across the coastal lowlands in geological pulses that transform entire forest ecosystems with each exhalation. These are not the familiar tides that will characterize later oceans, measured in hours and driven by lunar gravity, but vast changes in sea level that occur over thousands of years, driven by the expansion and contraction of ice sheets that form and melt at the planet's poles in response to orbital cycles that won't be understood until civilizations develop the mathematics to calculate celestial mechanics across millions of years. When the seas inhale, drawing water back toward polar ice caps that grow during periods of slightly cooler global temperatures, vast areas of shallow ocean floor emerge as new coastal plains ripe for forest colonization. The newly exposed landscapes stretch for hundreds of miles inland from previous shorelines, creating opportunities for the giant trees to establish new colonies on substrates still soft from their recent submersion. These emergent landscapes possess the perfect combination of mineral-rich sediments and high water tables that support the rapid growth of hollow giants reaching toward atmospheric oxygen concentrations that make such growth possible. The exposed seafloors bring with them chemical signatures that will influence coal formation for millions of years. Marine sediments contain different mineral compositions than terrestrial soils, providing unusual combinations of nutrients that affect both the growth rates of trees and the chemistry of preservation when those trees eventually fall into the swamps that develop across the emerging landscapes. Coal seams formed on these emergent marine platforms will possess distinctive chemical signatures that will allow future geologists to map the ancient shorelines with remarkable precision. When the seas exhale, expanding outward as polar ice caps melt and water levels rise across the globe, the advancing waters drown vast forests that may have grown for thousands of years during the previous low water period. The rising seas don't arrive as catastrophic floods, but as gradual increases in water level that may take decades or centuries to complete, allowing trees time to respond to changing conditions through altered growth patterns, while ultimately succumbing to root systems that cannot survive permanent submersion below their tolerance limits. The drowning forests create their own peculiar preservation environments. Trees that topple into rising seawater undergo different chemical transformations than those that fall into freshwater swamps, creating coal precursors with higher sulfur content and different mineral associations. Marine bacteria, suddenly finding themselves in contact with vast quantities of terrestrial organic matter, begin decomposition processes that proceed along pathways unknown in purely terrestrial or purely marine environments, creating chemical signatures that will puzzle future geochemists studying coal deposits with unusual elemental compositions. The cyclical nature of these sea level changes creates repetitive patterns in the geological record that will become some of the most distinctive features of Carboniferous stratigraphy. Coal seams alternate with marine limestone layers in sequences that repeat with mathematical regularity, creating what geologists will term cyclothems, repetitive rock sequences that record the breathing of ancient oceans across coastal landscapes. Each cycle preserves a complete environmental story, marine limestone recording high sea levels, followed by terrestrial sediments documenting the transition to land conditions, followed by coal seams representing the forests there that grew during low sea level periods, followed by marine rocks again as the seas return. The transitional zones where rising seas meet established forests create unique ecological environments that exist only during the periods of changing water level. Salt-tolerant plants begin to colonize the margins of forests, increasingly affected by saltwater intrusion, while freshwater-adapted trees retreat inland ahead of the advancing brine. These transition zones may persist for centuries as sea levels rise slowly enough to maintain gradual environmental gradients rather than sharp boundaries between marine and terrestrial conditions. Fish and marine invertebrates find themselves swimming through forests that still stand partially above water, creating temporary ecosystems where aquatic and terrestrial organisms interact in ways that will never be repeated in later geological epochs. Early fish navigate between tree trunks in water that may be only a few feet deep, while marine organisms colonize the submerged portions of root systems, creating unusual associations between marine animals and terrestrial plants that leave distinctive traces in the fossil record. The chemistry of these transitional waters creates its own preservation environments. Brackish conditions. Where fresh water from the forests mixes with salt water from the advancing seas, support bacterial communities different from those found in either purely fresh or purely marine environments. These specialized bacterial communities create unusual decomposition pathways that may contribute to the formation of coal types, with characteristics intermediate between those formed in purely terrestrial swamps and those influenced by marine conditions. Ocean circulation patterns themselves respond to the changing distribution of land and sea created by these cyclical drownings and emergences. When vast coastal plains emerge during low sea level periods, they alter wind patterns and ocean currents in ways that affect global climate systems. When rising seas flood these same areas, they create shallow epicontinental seas that warm more quickly than deep oceans, potentially influencing the atmospheric conditions that support the giant forests in the first place. The timing of these sea level cycles appears to correlate with orbital variations that affect the distribution of solar energy across Earth's surface, creating climate changes that influence the formation and melting of polar ice sheets. The mathematical precision of these orbital cycles ensures that the sea level changes occur with predictable rhythms, though individual cycles may vary in magnitude depending on how global climate systems respond to the astronomical forcing that drives them. Already, the most recent cycle shows signs of reaching another transition point. Sea levels that have remained relatively stable for thousands of years begin to show subtle changes that herald another major shift in the distribution of land and water across the coastal lowlands. The forests currently growing in the vast swamps may soon face either emergence onto drier ground or submersion beneath advancing seas, depending on whether the next phase of the cycle brings ice sheet growth or melting in the polar regions. The biological communities that have adapted to these cyclical changes possess strategies for surviving transitions that will seem almost impossible to organisms adapted to more stable environments. Some plant species maintain seed banks that can survive submersion for decades, germinating only when falling sea levels again expose suitable terrestrial habitats. Others develop growth forms that can tolerate gradual transitions from terrestrial to aquatic conditions, growing as terrestrial plants when young but adapting to increasingly waterlogged conditions as they mature. The breathtaking scale of these environmental changes dwarfs anything that later ecosystems will experience outside of the mass extinction events that punctuate geological history. Yet, the forests adapt to them as routine variations in environmental conditions, suggesting that the stability later ecosystems will require for their existence represents a deviation from rather than a continuation of the environmental variability that characterizes this epoch. The leaves that fall in these ancient forests descend into a silence deeper than any that will characterize later woodlands, settling into still waters that receive them without the familiar rustle of decay that announces autumn in seasonal climates. There is no autumn here, no coordinated shedding of foliage that marks the transition between growing seasons. Only the continuous rain of individual leaves dropping year-round from trees that have never learned the rhythms of dormancy. Each leaf falls alone, spiraling slowly through humid air thick enough to slow its descent, finally coming to rest on water surfaces that barely ripple with the gentle impact. The chemistry of preservation begins immediately upon contact with these oxygen-poor waters. Unlike the rapid decomposition that will characterize leaf fall in later forest ecosystems, where fallen foliage disappears within months or years through the combined action of bacteria, fungi, and invertebrate decomposers, these leaves enter an environment where decay proceeds so slowly that cellular structure remains intact for decades. The soft tissues break down gradually, but the more resistant components, the waxy cuticles that protected leaves from desiccation, the lignified veins that provided structural support, persist long enough to become incorporated into the sedimentary layers accumulating on the swamp floors. The leaf shapes themselves tell stories that will be read by paleobotanists hundreds of millions of years later. Lepidodendron leaves, narrow and grass-like, designed for maximum surface area in the low light conditions beneath dense canopies, preserve with such fidelity that individual stomata, the microscopic pores that regulate gas exchange, remain visible under electron microscopes. Seed fern fronds, with their delicate, lacy architecture, optimized for capturing the faint light that penetrates to the forest understory, flatten into carbon films that maintain their intricate patterns like pressed flowers in a geological herbarium. The continuous nature of leaf fall creates sedimentary patterns unlike those that will characterize seasonal forests. Instead of distinct layers that mark annual episodes of concentrated leaf drop, these swamp sediments show gradual accumulations of organic matter interrupted only by occasional floods that redistribute the accumulating material, or by the massive inputs of organic matter that occur when entire trees topple into the preserving waters. The result is a relatively homogeneous mixture of plant material from all levels of the forest canopy, preserving comprehensive samples of forest biodiversity in single sedimentary layers. The water itself becomes a preserving medium that maintains organic matter in states that will seem impossible to future scientists studying decomposition in oxygen-rich environments. Leaves that sink into the deeper, more oxygen-depleted zones of the swamps undergo a form of slow mummification, their cellular contents gradually replaced by dissolved minerals while their overall structure remains intact. This creates fossil preservation so detailed that scientists will be able to identify not just the species of plants, but their states of health, their responses to environmental stresses, even evidence of insect damage or disease. The acoustic environment of leaf fall differs markedly from the sounds that will characterize later forests. Without the crisp rustling of leaves hitting dry ground, without the crackling of brittle foliage being disturbed by wind or small animals, the falling leaves create only the softest of sounds, gentle plops as they break the surface tension of still water, followed by silence as they sink slowly into depths where no currents disturb their final resting places. The accumulated leaf layers on the swamp floor absorb sound so effectively that even large movements through the water create barely audible splashing. Decomposition chemistry in these waterlogged conditions proceeds along pathways that will disappear when later forests develop on better drained soils. Bacterial communities specialized for anaerobic environments break down proteins and simple carbohydrates while leaving more complex molecules intact, creating a selective preservation process that concentrates the most chemically stable components of plant tissues. This biochemistry produces unusual byproducts: methane, hydrogen sulfide, and organic acids that create water chemistry unlike anything that will exist in later forest ecosystems. The leaf chemistry itself reflects the unusual atmospheric conditions of this epoch. High carbon dioxide concentrations affect photosynthesis in ways that alter the ratios of different organic compounds within plant tissues, creating leaves with chemical signatures that will help future scientists reconstruct ancient atmospheric compositions. The absence of seasonal variations in temperature and light means that these leaves never develop the complex chemical defenses against environmental stress that will characterize foliage in more variable climates. Insect damage preserved in the falling leaves provides evidence of herbivory patterns that operate without seasonal constraints. Unlike later forests, where insect populations fluctuate dramatically with changing seasons, these carboniferous forests support continuous herbivory that proceeds at steady rates throughout the year. The damage patterns preserved in fossil leaves show both the feeding activities of giant insects and the plant responses to continuous browsing pressure, chemical defenses, and structural modifications that reflect evolutionary arms races conducted over geological timescales. The mineral content of the preserving waters affects which aspects of leaf structure survive the fossilization process. Waters rich in silica create different preservation conditions than those with high iron content, leading to fossils that emphasize different aspects of original plant anatomy. Some leaves preserve as detailed carbon films that show cellular structure, while others become mineralized replicas that maintain three-dimensional form while losing fine structural detail. The stratification of leaf preservation within individual swamps creates vertical gradients in fossil quality that reflect the chemistry of different water depths. Leaves that settle into the deepest, most oxygen-poor zones undergo the most complete preservation, while those that remain in shallower water experience partial decomposition that removes some structures while preserving others. This creates fossil assemblages where different aspects of plant anatomy are preserved at different levels within the same sedimentary sequence. Temperature variations, subtle as they are in this greenhouse climate, affect the rate of preservation chemistry in ways that create seasonal signals even in the absence of true seasons. Slight warming during summer months accelerates bacterial activity enough to alter preservation patterns, while the marginally cooler conditions of winter slow decomposition sufficiently to create different fossil preservation styles. These subtle variations create layered preservation patterns that will help future geologists identify climatic rhythms in apparently uniform sedimentary sequences. Already, some of the leaf fossils forming in the deepest parts of these swamps show the chemical changes that represent early stages of coal formation. The organic molecules that give leaves their structure begin the slow transformation that will eventually produce the coal deposits that power industrial civilizations. But the process proceeds so gradually that intermediate stages preserve recognizable plant anatomy for millions of years before finally completing the transformation to pure carbon. The silence that receives each falling leaf accumulates its own geological weight, building layers of quietude that will be preserved in stone along with the plant material itself. Future scientists examining these fossil deposits will find not just the remains of ancient plants, but evidence of the profound stillness that characterized these forests, where the sounds of later forest ecosystems, wind in deciduous leaves, the movements of large animals, the seasonal migrations of birds, simply did not exist. Beneath the patient swamps, continents drift toward their inevitable collision with the slow inevitability of geological time, carrying their cargo of giant forests across ocean basins that shrink by inches each year. Pangaea, the supercontinent that will dominate Earth's geography for the next 100 million years, assembles itself through the convergence of land masses that began their journey when the first primitive plants were still learning to survive on land. The forests growing now exist in the breathing spaces between continents, in the lowlands that will be compressed and elevated when the great collision finally brings all land together into a single, vast continent surrounded by a single, vast ocean. The movement itself proceeds too slowly for any living organism to detect, yet its effects ripple through the forest ecosystems in ways that will determine the future of coal formation and climate across the globe. As continents approach each other, the shallow seas that separate them gradually narrow, altering ocean circulation patterns that have maintained the greenhouse conditions necessary for the giant trees. Deep ocean currents that once carried warm water to polar regions find their pathways blocked by converging landmasses, beginning changes in global heat distribution that will eventually transform the climate systems that support these swamp forests. Mountain building begins along the collision zones where continental margins slowly buckle under the immense pressures of convergence. The Appalachian Mountains rise grain by grain along the eastern margin of what will become North America, their elevation increasing so gradually that erosion keeps pace with uplift for millions of years, creating a balance between construction and destruction that maintains steady inputs of sediment to the coastal lowlands where the forests grow. These sediments provide the mineral nutrients that support rapid tree growth, while contributing to the geological foundations that will preserve the forests as coal deposits. The assembly of Pangaea creates its own feedback loops that affect atmospheric chemistry and climate stability. As continents merge, the total length of continental margins decreases, reducing the areas where shallow seas can moderate global temperatures through evaporation and heat absorption. The climate systems that have maintained the stable greenhouse conditions necessary for year-round forest growth begin to show the first signs of instability that will eventually lead to the seasonal variations that characterize later geological epochs. Volcanic activity increases along the collision zones, adding carbon dioxide to the atmosphere while simultaneously creating new mountain ranges that alter wind patterns and precipitation distribution. The volcanic emissions may help maintain the high atmospheric carbon dioxide concentrations that support the rapid growth of the giant trees, but the changing topography created by mountain building begins to disrupt the atmospheric circulation patterns that distribute moisture evenly across the vast coastal lowlands. The convergence of continents also affects sea level patterns by altering the volume of ocean basins. As continents collide and create mountain ranges, they displace seawater that must be accommodated elsewhere, contributing to the cyclical sea level changes that alternately drown and expose the forest-covered lowlands. The mathematical precision of these changes reflects the mechanical inevitability of continental collision combined with the orbital cycles that affect global ice volume at the poles. Deep beneath the accumulating organic matter in the swamps, the collision of continents creates the pressure and temperature conditions that will transform buried plant material into coal over geological timescales. The slow compression that accompanies continental convergence provides exactly the conditions necessary for the chemical transformations that convert preserved wood into the concentrated carbon that will fuel industrial civilizations hundreds of millions of years in the future. Without this continental collision, the organic matter accumulating in the swamps might never achieve the pressures necessary for coal formation. The changing paleogeography also affects the evolution of the forests themselves. As continents approach each other, previously isolated forest communities come into contact, allowing genetic exchange between plant populations that may have been separated for millions of years. This genetic mixing creates opportunities for evolutionary innovations that wouldn't be possible in completely isolated populations, potentially contributing to the remarkable diversity of tree species that characterize Carboniferous forests. Ocean chemistry changes as circulation patterns are disrupted by the converging continents. Waters that once circulated freely between ocean basins find themselves increasingly isolated, developing different chemical signatures that affect the preservation of organic matter when marine conditions temporarily flood the coastal forests. These chemical changes may contribute to variations in coal quality that will be discovered when future civilizations begin mining the deposits formed during this epoch. The approach of continents also begins to affect atmospheric circulation patterns in ways that will eventually break up the stable climate conditions that support the giant forests. The formation of large continental masses creates opportunities for seasonal temperature variations as land surfaces respond more rapidly to changes in solar heating than ocean surfaces do. These seasonal variations remain subtle for now, but they represent the beginning of climatic changes that will eventually make year-round forest growth impossible across much of the continental interior. A climate modeling of this epoch reveals that the assembly of Pangaea creates a natural experiment in global climate stability. The gradual transition from a world of separated continents surrounded by ocean to a world dominated by a single large landmass tests the limits of how much continental configuration can be altered before fundamental changes in climate systems become inevitable. The forests growing now exist during the final stages of a continental arrangement that has supported stable greenhouse conditions for millions of years. The biological communities of the forests begin to show subtle responses to the changing environmental conditions created by continental convergence. Some tree species develop slightly deeper root systems, possibly in response to increasing seasonal variations in soil moisture that reflect the early stages of climate change. Others show changes in leaf architecture that may represent adaptations to subtly different light conditions created by increasing atmospheric dust from volcanic activity along the collision zones. The timing of the continental collision appears to be synchronized with other global changes that will affect the long-term survival of the giant forests. Ice sheets at the poles show signs of expansion that may be related to changes in ocean circulation created by the converging continents. While atmospheric chemistry models suggest that the volcanic activity associated with mountain building may begin to alter the balance of gases that has maintained optimal conditions for plant growth. Already, some forest communities in areas closest to the zones of continental collision show evidence of environmental stress that may herald larger changes to come. Trees in these regions grow more slowly and achieve smaller maximum sizes than their counterparts in areas still buffered from the effects of continental convergence, suggesting that the assembly of Pangaea will eventually create environmental conditions incompatible with the growth strategies that have made the giant forests possible. The spaces between converging continents represent more than just geographical features. They are temporal zones where one type of global system gradually transforms into another. The forests growing in these spaces exist in the transition between the multi-continental world that has supported stable greenhouse conditions and the supercontinental world that will eventually develop seasonal climates too variable for year-round forest growth. The climate breathes with slower rhythms now. Subtle changes in temperature and precipitation patterns that herald the end of the endless greenhouse that has supported these forests for millions of years. The shifts occur so gradually that individual trees complete their entire lifespans without experiencing dramatic environmental changes. Yet the cumulative effects of these climatic variations begin to alter the fundamental conditions that have made giant hollow trees possible across vast continental areas. What begins as minor fluctuations in seasonal rainfall will eventually transform into the pronounced wet and dry periods that will make year-round swamp forests impossible across most of the continental interior. The first signs appear in the growth patterns of trees growing at the margins of the great swamp forests, where environmental conditions remain most sensitive to climatic variations. These trees show subtle changes in their leaf scar patterns that reflect responses to brief, dry periods that interrupt the constant moisture that has characterized this epoch. The dry periods may last only weeks or months, insignificant compared to the droughts that will characterize later climates, yet they represent the beginning of seasonal patterns that will eventually govern all terrestrial ecosystems. Atmospheric circulation patterns shift as the assembly of Pangaea alters the distribution of land and sea across the globe. The vast interior regions of the converging supercontinent begin to experience continental climate effects that have been unknown during the millions of years when smaller continents were surrounded by moderating ocean influences. Summer temperatures in these interior regions rise slightly higher than the constant warmth that has previously characterized all seasons, while winter temperatures drop just enough to slow plant growth and create the first suggestion of dormancy periods that will become essential for survival in seasonal climates. The ice sheets that form at the poles during cooler periods in the orbital cycles begin to persist longer than they have in previous cycles, reflecting both the cooler conditions created by changing ocean circulation and the reduced ability of continental interiors to moderate temperature extremes. These ice sheets lock up increasing amounts of water that would previously have maintained the high sea levels necessary for extensive coastal swamps, beginning the process of environmental change that will eventually drain most of the wetlands where coal formation occurs. Precipitation patterns across the great forests show the first signs of developing seasonal rhythms. Instead of the steady, year-round rainfall that has maintained constant soil moisture for millions of years, some regions begin to experience subtle variations where certain months receive more rainfall than others. These variations remain minor, the difference between very wet and extremely wet conditions, but they create the first environmental pressures that select for plants capable of surviving brief periods of reduced water availability. The giant trees themselves begin to show adaptive responses to these changing conditions. Some species develop slightly thicker bark that provides better protection against the minor temperature fluctuations that accompany the developing seasonal patterns. Others show changes in their leaf architecture that may represent early adaptations to the increased light availability that results when brief dry periods thin the forest canopy through increased tree mortality. These changes occur slowly enough that they might represent normal evolutionary variation rather than responses to environmental change. Yet their timing suggests that natural selection has begun to favor characteristics that will prove essential for survival in more variable climates. The chemistry of coal formation reflects these climatic changes in ways that will be detected by geochemists studying coal deposits hundreds of millions of years later. The ratios of different organic compounds preserved in the accumulating plant material change subtly as trees adapt their metabolism to cope with environmental variation, creating chemical signatures that record the transition from stable greenhouse conditions to the more variable climate that will characterize the later Carboniferous period. Ocean temperatures begin to show seasonal variations in regions where ocean circulation has been disrupted by the convergence of continents. These temperature changes affect evaporation rates and precipitation patterns over adjacent land areas, creating feedback loops between marine and terrestrial climate systems that amplify the effects of relatively minor changes in atmospheric circulation. The stable climate system that has maintained greenhouse conditions for millions of years proves more sensitive to disruption than its long stability might suggest. The timing of these climate changes appears to be accelerating as multiple factors converge to create environmental conditions that differ increasingly from those that supported the initial establishment of the giant forests. Continental collision continues to alter global geography. Ice sheet dynamics respond to changing ocean circulation, and atmospheric chemistry begins to shift as volcanic activity changes the inputs of greenhouse gases to the atmosphere. The intersection of these multiple factors creates a rate of environmental change that will soon exceed the ability of forest ecosystems to adapt through gradual evolutionary modification. Some forest communities respond to the changing conditions by shifting their geographical distributions, with species that require the most stable moisture conditions retreating toward coastal areas where marine influences continue to moderate climate variations. Others begin to show evidence of reproductive stress as the environmental cues that have triggered reproduction for millions of years become less reliable in the face of developing seasonal variations. These biological responses create the first signs of ecosystem instability that will eventually lead to the replacement of the giant forest communities by vegetation adapted to more variable environmental conditions. The preservation chemistry in the swamps also responds to the changing climate conditions. Brief dry periods that lower water levels in some wetlands expose previously submerged organic matter to oxygen, halting the preservation process and creating gaps in the geological record that will mark the beginning of the end of the coal-forming epoch. These interruptions in preservation remain localized and brief, but they represent the beginning of environmental changes that will eventually end the unique combination of conditions necessary for large-scale coal formation. Atmospheric models of this transition period suggest that the climate system approaches a threshold beyond which the greenhouse conditions that have characterized this epoch become impossible to maintain. The mathematical relationships between atmospheric chemistry, ocean circulation, and continental configuration that have supported stable warm conditions prove to be more delicate than the millions of years of climate stability might suggest, operating within narrow ranges that will be exceeded as continental assembly continues. The forests growing now represent the last generation of giant trees that will experience the climatic conditions that made their evolution possible. The environmental changes already underway will create selection pressures that favor smaller trees with deeper root systems and more efficient water use strategies, beginning the evolutionary transition toward forest communities adapted to the seasonal climates that will dominate Earth's later history. Already, the seeds of change germinate in scattered locations where brief dry periods have created openings in the forest canopy. New types of plants, better adapted to variable moisture conditions, begin to establish themselves in these gaps, representing the first invasion of seasonal vegetation into ecosystems that have known only constant growing conditions for millions of years. The final giants stand in isolation now, their hollow crowns rising above wetlands that shrink with each passing millennium as the great climatic transition accelerates toward its inevitable conclusion. These last-scale trees grow in the remaining refugia where ancient conditions persist, scattered swamps and coastal lowlands where marine influences still moderate the developing seasonal extremes. Islands of the Carboniferous world surrounded by landscapes increasingly dominated by vegetation adapted to the drier, more variable conditions that herald the approach of a new geological epoch. The lepidodendron and sigillaria that still achieve their ancestral heights grow with a desperate magnificence, their diamond-patterned bark catching light that filters through canopies, increasingly punctuated by gaps where fallen giants have not been replaced by new growth. The chemistry of preservation that once turned fallen trees into coal precursors with perfect fidelity now operates sporadically, interrupted by dry periods that expose organic matter to oxidation and decay. The geological libraries that have accumulated the stored sunlight of millions of years will soon close their final chapters, their last pages written in the compressed remains of these final forest stands. The remaining forests exist as living museums of conditions that will never return to Earth's surface. The atmospheric oxygen concentrations that support giant insects continue to decline slowly as organic matter burial decreases and oxidation of previously preserved carbon increases. The dragonflies with 3-foot wingspans become increasingly rare, their populations restricted to the few remaining areas where air density still supports their impossible proportions. Within another few million years, the insects that patrol these forest corridors will have shrunk to sizes that seem modest compared to the giants that once dominated Carboniferous skies. Scientific analysis of these final forest communities reveals evolutionary adaptations that represent last-minute attempts to cope with changing environmental conditions. Some trees develop more extensive root systems that probe deeper into soil layers in search of stable moisture supplies, while others modify their leaf chemistry to cope with the increasing frequency of drought stress. These adaptations prove too little and too late to prevent the fundamental changes that will transform forest ecosystems across the globe, but they preserve evidence of how plant communities respond to environmental transitions that exceed their adaptive capacity. The timing of forest decline varies across different geographical regions, creating a complex mosaic of ecological change that unfolds over several million years rather than occurring as a single catastrophic event. Forests in coastal areas where marine influences continue to moderate climate variations persist longer than those in continental interiors, while forests growing at higher latitudes experience different pressures than those near the equator. This geographical variation in the timing of change creates opportunities for some plant species to survive by migrating toward areas where favorable conditions persist longer. Fossil preservation during this transition period creates its own unique signatures that will help future paleontologists understand exactly how the transformation occurred. The chemistry of coal formation changes as preservation conditions become less optimal, creating deposits with different characteristics than those formed during the peak of the coal-forming epoch. Some of the final coal seams show evidence of repeated interruptions in the preservation process, creating layered deposits that record multiple cycles of burial and exposure as climate conditions fluctuated around the threshold, values necessary for successful organic matter preservation. The ecological relationships that have characterized these forest ecosystems for millions of years begin to break down as key species disappear from communities that lose the environmental conditions necessary to support them. The complex networks of plant-fungal partnerships that have supported the giant trees prove unable to function under the more variable moisture conditions, while the specialized bacterial communities that have created unique soil chemistry in the waterlogged swamps cannot survive the periodic exposure to oxygen that accompanies increasing climate variability. Some plant lineages respond to the changing conditions by evolving in directions that will characterize later forest ecosystems. Early representatives of coniferous trees begin to appear in the transitional communities, their needle-like leaves and deep root systems better adapted to surviving periodic drought than the broad, thin leaves and shallow roots that have characterized the giant scale trees. These evolutionary innovations represent the beginning of forest strategies that will dominate terrestrial ecosystems for hundreds of millions of years. The final collapse of individual forest stands often occurs quite rapidly once environmental conditions cross critical thresholds, creating dramatic changes in local ecosystems within periods measured in centuries rather than millennia. Trees that have grown successfully for hundreds of years suddenly find themselves unable to reproduce successfully as their seedlings fail to establish in the changing soil chemistry of drying swamps. Without successful reproduction, these communities age toward extinction as existing trees reach the end of their lifespans without replacement. The last major coal deposits formed during this transition period, preserving not just the remains of the final giant forests, but also evidence of the environmental conditions that brought their era to an end. Future geologists will find within these deposits a detailed record of how climate change affects forest ecosystems, providing insights into ecological processes that will prove relevant when later civilizations face their own periods of rapid environmental change. Atmospheric chemistry continues to evolve as the burial of organic matter that has maintained high oxygen concentrations for millions of years slows and finally stops in most regions. The oxygen-rich atmosphere that has supported giant insects and rapid plant growth gradually returns toward the more moderate concentrations that will characterize Earth's later history. This atmospheric transition occurs slowly enough that most organisms can adapt through evolutionary change, but quickly enough that the unique ecological opportunities of the Carboniferous epoch disappear forever. The seas continue their cyclical rising and falling, but the advancing waters now encounter landscapes increasingly covered by vegetation adapted to periodic exposure rather than the constantly waterlogged forests that once covered vast coastal areas. The drowning episodes that once created perfect conditions for coal formation now simply create temporary marine environments that revert to terrestrial conditions without leaving behind the massive organic deposits that characterized earlier cycles. Some isolated swamps continue to function as coal-forming environments for several million years after the great forests have disappeared from most regions, creating final deposits that preserve evidence of the last communities of giant-scale trees. These final refugia serve as evolutionary laboratories where the descendants of Carboniferous plants experiment with adaptations that will allow some lineages to survive into the new climatic regime, while others face extinction as their environmental requirements become impossible to meet anywhere on the changing planet. The silence that settles over the former forest landscapes differs qualitatively from the profound quiet that characterized the living giant forests. Where once the creaking of hollow wood and the gentle splash of falling leaves created soundscapes of organic architecture, now only the wind moves through increasingly sparse vegetation adapted to the drier conditions that will define the post-Carboniferous world. Time flows differently now through landscapes where the memory of giants sleeps beneath layers of sediment that will harden into the stone archives of a world that once was. The last of the great hollow trees have fallen into swamps that themselves are disappearing, leaving behind only the compressed dreams of forests that touched skies no modern tree will ever reach. In the deep places where oxygen fears to venture, chemistry continues its patient work, transforming wood into coal, bark into black diamonds, the cellular architecture of ancient giants into the concentrated sunlight that will one day power civilizations that exist now only as evolutionary potential in the genes of early amphibians. The coal seams that form in these final years of preservation represent more than geological curiosities. They are libraries written in compressed carbon, encyclopedias of an epoch when Earth experimented with possibilities that will never arise again. Each layer preserves not just the physical remains of trees and ferns and mosses, but the atmospheric conditions that made their existence possible, the climate patterns that supported their growth, the very chemistry of air and water that sustained ecosystems unlike any that will follow in the fossil record. Deep within these forming coal deposits, the molecular fossils that will astonish future scientists continue their slow transformation from the organic compounds that once flowed through living cells into the stable carbon matrices that can survive for hundreds of millions of years. Proteins fold into configurations that will preserve amino acid sequences, while lignin polymers rearrange themselves into crystal structures that maintain the memory of wood grain and bark texture with microscopic fidelity. The chemistry of preservation operates as a form of geological photography, capturing moments from an ancient world with resolution that will seem impossible to future scientists studying rocks that preserve cellular detail. The atmospheric oxygen that once supported dragonflies with eagle-sized wingspans continues its slow decline toward the more modest concentrations that will characterize Earth's later history. As oxygen levels moderate, the fundamental rules of biology shift in ways that will make the giant arthropods of this epoch seem like creatures from an alien planet. The physics of respiration, of combustion, of all the chemical processes that sustain life, adjust gradually to new equilibrium conditions that will support different types of organisms with different strategies for extracting energy from their environment. Continental drift continues its inexorable assembly of Pangaea, bringing together land masses that carry the fossil evidence of their separate evolutionary histories toward collision zones, where mountain building will eventually expose the coal deposits formed in these ancient swamps. The Appalachian Mountains that rise along these collision boundaries will one day yield the compressed remains of these forests to civilizations that burn them for energy, completing chemical cycles that span hundreds of millions of years as carbon returns to the atmosphere from which it was once captured by photosynthesis in trees taller than buildings. The ice sheets that form at the poles during the cooler phases of orbital cycles grow thicker and more persistent as ocean circulation patterns continue to change in response to continental convergence. These ice sheets lock up water that would once have maintained the high sea levels necessary for extensive coastal swamps, beginning the long process of environmental change that will eventually drain most of the wetlands where coal formation occurs. The mathematical precision of orbital cycles ensures that these changes occur with predictable rhythms, though the magnitude of each cycle varies as global climate systems respond to the gradual assembly of the supercontinent. In the remaining pockets where ancient conditions persist, the last communities of giant-scale trees continue their patient growth toward canopies that will never again be achieved by terrestrial vegetation. These final forests exist as evolutionary anachronisms, living representatives of growth strategies that made sense only under the unique atmospheric and climatic conditions of this epoch. Their continued existence in scattered refugia preserves the genetic potential for giant growth, though that potential will never again find environmental conditions suitable for its expression. The geological record being written in these final coal-forming swamps will provide future scientists with detailed information about how ecosystems respond to environmental change that exceeds their adaptive capacity. The transition from coal-forming to non-coal-forming conditions preserves evidence of ecological thresholds, of the specific combinations of atmospheric chemistry, climate stability, and geological conditions necessary to support the unique type of preservation that has characterized this epoch. Climate models of this transition period reveal that Earth's atmospheric and oceanic systems approach new equilibrium conditions that will prove stable for the next several 100 million years. The greenhouse climate that has supported constant forest growth for millions of years gives way to more variable conditions that will eventually support the evolution of deciduous trees. Seasonal migration patterns, and all the biological strategies that characterize life in climates with pronounced seasonal variations. The chemistry of the atmosphere itself tells the story of this transition through isotopic signatures that will be preserved in rocks formed during this period. The ratios of different carbon isotopes reflect changes in the balance between organic matter burial and oxidation, while oxygen isotope ratios record changes in global temperature and ice volume that accompany the climatic transition. These chemical signatures create geological clocks that will allow future scientists to correlate the timing of environmental changes across different continents and ocean basins. As the last giants fall and the final swamps drain, The Carboniferous epoch draws toward its close with changes so gradual that individual organisms experience them as normal environmental variation rather than as the end of an entire chapter in Earth's history. The trees that fall now settle into preservation conditions that will prove adequate to maintain their forms for geological time. But the environmental conditions that allowed such trees to grow in the first place fade into geological memory. The silence that follows the end of active coal formation differs from the living silence that characterized the giant forests. It carries the weight of geological time, the quiet of chemical processes that operate below the threshold of biological awareness, the patient transformation of organic matter into mineral deposits that will outlast the continents on which they form. Somewhere in the accumulating sediments, the cellular remains of the last lepidodendron begin their transformation into coal, carrying with them the chemical memory of atmospheric oxygen concentrations that will not return for hundreds of millions of years. Their hollow cores, once filled with the air of an ancient atmosphere, slowly fill with minerals that preserve the exact dimensions of spaces that once echoed with sounds no future forest will make. The seeds of change that will characterize Earth's next chapter already germinate in the disturbed soils where seasonal climates begin to select for entirely different survival strategies. But for now, in the deep quiet of forming coal seams, the giants rest in geological sleep, their dreams compressed into carbon libraries that will wait hundreds of millions of years for readers who can decipher the stories written in stone. The deep quiet settles now into layers of stone and carbon, where time moves in the slow heartbeat of geological transformation. The forests that once reached toward impossible heights have found their final rest in the patient chemistry of coal formation. Their hollow towers compressed into seams of black that will sleep for hundreds of millions of years before human hands discover the stored sunlight of an epoch when trees were taller than buildings. In the darkness beneath accumulating sediments, the cellular architecture of giants undergoes its final metamorphosis from wood to stone to coal. Each molecular transformation proceeding at the pace of continental drift, each chemical change marking another step in the alchemy that converts ancient atmospheres into concentrated energy. The diamond patterns of bark become fossil textures. The hollow cores fill with minerals that preserve the exact dimensions of spaces where air once moved through living architecture. The silence here surpasses any quiet that walking creatures will ever experience. It is the silence of deep time, of processes so slow they occur below the threshold of awareness, of chemical reactions that require millennia to complete single steps. No footfall will disturb these resting places for epochs measured in hundreds of millions of years. No sound will penetrate depths where pressure and temperature work their patient magic on the remains of trees that knew skies no future forest will reach. The compressed dreams of Carboniferous giants rest now in geological sleep, their memories preserved in carbon libraries that record atmospheric compositions, climate patterns, and growth strategies from a world where oxygen-drunk air supported possibilities that will never arise again. Their stories lie written in the molecular structure of coal, waiting for civilizations that will eventually read these stone archives and marvel at evidence of forests that achieved heights modern trees can only dream. The breathing of continents continues its ancient rhythm above these sleeping forests, mountains rising and falling in cycles that will expose and bury the coal seams again and again across deep time. Ocean levels rise and fall to rhythms older than complex life, while ice sheets advance and retreat across poles that drift slowly around a planet, still learning the delicate balance between stability and change. And in the deepest quiet, where time itself seems to pause in respect for the magnitude of what has been preserved, the last echoes of hollow wood settle into silence that will outlast the erosion of mountains, the opening and closing of ocean basins, the very configuration of continents, on a world where the memory of giants sleeps in stone, waiting for the distant day when their stored energy will again reach toward light. The stillness deepens into geological rest, where dreams of 100-foot trees compress into carbon seams that hold the secret of when Earth grew forests taller than any building human hands will construct, when time moved differently through air thick enough to support the impossible, when the world held its breath and grew giants that touched the sky,